The graphical method is a method that can be used to solve two-dimensional linear programs. So linear programs with two decision variables. We will start to illustrate this graphical method by using the following example. So we will consider a manufacturing firm. This manufacturing firm is producing two types of products. For type 1 we can at most produce 4 products a day, and for type 2 at most 5. We also have a certain amount of time available, 9 hours per day available. In order to produce a product of type 1 it takes 2 hours, and for type 2 it takes 1 hour per product. And we can only produce one product at the same time. The income of producing a product of type 2 is twice as high as the income of producing a product of type 1. And then the question is how much should we produce of both of the product types in order to maximize the total income. If we are going to formulate a linear program, then we start with the decision variables. So we will use x1 and x2 for the two products, the amounts that we produce of the two product types. And then we will have the corresponding linear program. So the objective function is to maximize x1 plus 2 times x2. So the 2 because profit or the income for product type 2 is twice that of product type 1. We have functional constraints. We can produce at most 4 products of type 1, at most 5 products of type 2, and then we have 9 hours available, where we need 2 hours for product 1 and 1 hour for product 2. And we can of course not produce negative quantities, so we should also not forget the non-negativity constraints. And then the next question is, how can we now use this, or how can we now solve this problem graphically? In order to do that, we first draw the feasible solution space. That means that we first have the non-negativity constraints, and that implies that solutions can only be in this area. So in the area where both decision variables take a non-negative value. Then we are also going to add the functional constraints to this. So the first functional constraint is x1 is smaller than or equal to 4. That means that only points to the left of the constraint boundary x1 equals 4 are allowed. So this narrows the feasible solution space. x2 should be smaller than or equal to 5. So if we draw the line x2 is equal to 5, then only points below that line are feasible. So this again narrows the feasible solution space. And then the third functional constraint is 2x1 plus x2 should be smaller than or equal to 9. You see in the figure the constraint boundary, and only points to the left and below that line are allowed. We can draw that constraint boundary. Basically, if you have 2 points on the constraint boundary, then you can just connect those 2 points and then you have the constraint boundary because it's linear. So if you have 2 points, then you basically have that linear or that straight line. You can also express x2 in terms of x1. So the constraint boundary is given by 2x1 plus x2 is equal to 9. If we subtract 2x1 from both sides, what we then get is this. And then you basically have x2 as a function of x1. And this is then the corresponding graph of that function. So that's also how we could do this. So this is the feasible solution space. The next question is now, which solution in this feasible solution space is the optimal solution? Because that's what we are looking for. So we would like to find values for x1 and x2 such that we are still in the feasible solution space and such that the value for z is maximized. The method that we can use is we can again express x2 as a function of x1 and now also as a function of z. So we bring everything to the right hand side except for the x2, and then we isolate x2. So what we basically do, if we have this, and you could say that we subtract x1 from both sides, and then the second step is that we divide both sides by 2, so then we will get this. So then you have exactly what is also written over here. So this is x2 as a function of x1 and as a function of z, and this is called the slope-intercept form of the objective function. If we now replace z by a random value, then we can draw the corresponding graph, and that graph gives you then all the points that result in that value for z. So for instance, if you fill in for z number 2, the value 2, then this is what you will get. So it's a half times 2 is 1. And now you can draw the graph of this line, and that's what you also see in the figure. And then you get all points where z is equal to 2. And you see that there are also feasible points where z is equal to 2. So z equal to 2 can be reached. Let's then also try another value for z. So let's also try z is 8. And this is what we will get. You can again draw the corresponding graph. And then you see again that there are points where z is equal to 8. So z is equal to 8 can also be reached. Next one is 14. But then you see that we don't have an intersection with the feasible solution space anymore. That means that there are no feasible solutions where z is 14. So z is 14 cannot be reached. There's maybe also something else that you realize by considering this figure, and that's that all those lines are parallel. So all those lines for certain fixed values for z are all parallel. And you also see that the only thing that you need to do to get a better value for z, in this case, is to move the line upwards. And then the question is, how far can you move it upwards in such a way that we still have a point in common with the feasible solution space. So we move it upwards. Question now is, how far can we move it upwards? From this figure, you can see that you can move it upwards until the point where you only have one point in common with the feasible solution space anymore. So this is basically how the graphical method works. Checking how far you can move the line for fixed value of z in the direction where the solutions get, where the value gets better. So we can move it upwards until this point. And then this is the optimum solution. If you would like to increase z further, then that's not possible, because then you don't have any points in common with the feasible solution space anymore. So that's the optimal solution, the point that is indicated here. Here you can immediately see that it's x1 is 2 and x2 is 5. We can also determine that algebraically. So if we are at this point, then we are at the intersection of the line x2 equals 5, and the other line is 2x1 plus x2 is equal to 9. So you basically have two equalities with two unknowns that can be solved, and then you will also find that this is then the optimal solution. So x1 is 2 and x2 is equal to 5. The corresponding value for z is 12. So you have an optimum solution and you have a corresponding optimum value. And indeed 14 cannot be reached. That's what we already realized. The highest value for z that can be reached is the 12. So that's what you see over here. So in this case we have that the optimal solution is unique. That's not always the case. It can also be like what we see over here. So this is just another example. We already have the feasible solution space drawn. It's a bit more complicated because we have two functional constraints that contain both variables, and also the numbers are a little bit more complicated. You can try to draw this feasible solution space by yourself. So based on these constraints, you can try to draw this feasible solution space. And then the next step, if you solve it, is to fix z and draw all solutions that give that value for z, and then to check how far you can shift that line in the right direction. If we do that here, then this is what we will get. So you see that this line for fixed values of z has been moved to the right until the point where we are right now, because if you move it further to the right, then we don't have any points in common with the feasible solution space anymore. And now you see also that there are infinitely many optimal solutions. So this is an optimal solution, this is an optimal solution, but also all points in between are also optimal solutions. So here we have infinitely many optimal solutions. And that's related to corner points. So what we see here is that we have two corner points that are optimal. All points in between are also optimal. We can also give that entire set mathematically. So we have an optimal corner point is, so let's write that down, optimal corner points. The first one is x1 is equal to 3 and x2 is equal to 5. The second one is x1 is equal to 4 and x2 is equal to 3. And then all convex combinations of those two corner points are also optimal solutions. A convex combination means alpha 1 multiplied by the first solution and then 1 minus alpha 1 multiplied by the second solution. So if you have 2 points, a feasible solution, you can call it alpha 1, you can also just call it alpha. So if we multiply the first solution by alpha, the second solution by 1 minus alpha, and alpha should then should be in between 0 and 1. If you do that, then you will get another optimal solution. So if we multiply the first solution by alpha, then you get 3 alpha plus 4 times 1 minus alpha. That will be the value for x1. And this gives us 3 alpha minus 4 alpha is minus alpha, and we have the 4. And x2, so the first, the 5 is multiplied by alpha, the 3 is multiplied by 1 minus alpha, and this gives us 5 alpha minus 3 alpha is 2 alpha plus 3, so 3 plus 2 alpha. This is an optimal solution for any alpha in between 0 and 1. So any convex combination of those two corner points is also optimal. I was already talking about corner points. So what is a corner point? Here you see two examples of corner points. There are more corner points over here. So 5 corner points of the feasible solution space in total. A corner point in general is a point that lies at an intersection of at least n constraints. N is the dimension of the problem, and the dimension of the problem is the number of decision variables. So if you have 2 decision variables, then this is 2. So then a corner point lies at an intersection of at least 2 constraints. It's at least 2 constraints because you can also have a third constraint that also intersects these points. So then you see that the corner point can also be at the intersection of 3 constraints. So it is at least n constraints. And for this 2-dimensional case, is at least 2 constraints. So if you have a problem with 3 decision variables, then you need an intersection of at least 3 constraints in order to have a corner point. If there is an optimum solution, because not all linear programs have an optimum solution, but if there is an optimum solution, then the best feasible corner point must be an optimum solution. So that's also what we have seen here. There is an optimum solution, and then we have 2 corner points that have the best value for z, then those 2 must be optimal solutions. So it cannot be that there are optimal solutions, but that there are no corner points that are optimal. Another thing is that if you have exactly one optimum solution, then it must be a corner point that is optimal. And if you have multiple optimum solutions, then there will always be at least 2 that corresponds to corner points. And then if you have multiple optimum solutions, then we have also seen that there are infinitely many optimum solutions. So this is an example for a 3-dimensional linear program where we have 3 corner points that are optimal. And now the question is to determine all optimum solutions of the LP. If there are multiple corner points that are optimal, then any convex combination of these corner points is then also optimal. And if you have 3 points, then you cannot use the approach with alpha and 1 minus alpha anymore. So what we should do here is we should multiply the first solution by alpha 1, the second one by alpha 2, and the third one by alpha 3. If you choose those alpha values non-negative in such a way that the sum of them is 1, then you have a convex combination of the 3 solutions. So what we then get is that x1, so we have 2 times alpha 1 plus alpha 2 plus alpha 3. We get x2, and then you again have that the first solution is multiplied by alpha 1, the second one is multiplied by alpha 2, and the third one is multiplied by alpha 3. And x3 will be alpha 2 plus 4 times alpha 3. And this is an optimum solution for any alpha 1, alpha 2, alpha 3, all greater than or equal to 0, and the sum of them should be 1. So this is the definition of a convex combination of 3 points in a 3-dimensional plane. So this gives us mathematically the set of all optimum solutions. Again, so what are the steps if you are trying to use the graphical method to solve a 2-dimensional linear program? Then we are first drawing the constraint boundary for each constraint, and then we need to check on which side of each constraint boundary we have the feasible solution space. And based on that, we then have basically the entire feasible solution space. Then we are going to determine the slope of the objective line, and we draw the objective line for an arbitrary value of z. Then we need to check in which direction we need to move that objective line in order to get a better value for z. And better can be higher if you have a maximization problem, but it's lower if you have a minimization problem. And then we should move that line in that direction as far as we can, but in such a way that we still have points in common with the feasible solution space. So then we basically have the optimum solution. So one more example to illustrate this. The idea is the same. It's a bit more complicated here because you have some negative numbers. The idea is just the same. So let's start with the feasible solution space. So x1 minus x2 should be smaller than or equal to 1. The constraint boundary is the same, but then exactly equal to 1. If you have 2 points on that constraint boundary, so for instance 1, 0 and 2, 1, those are clearly on the constraint boundary. So if you have those 2 points and you connect those 2 points, then you have the constraint boundary. And then in order to determine on which side of the constraint boundary we have the feasible solution space, you can just check 1 point. So you can, for instance, check the point 1, 1. The constraint is satisfied at 1, 1. So that means that the feasible solution space should be to the left and above this constraint boundary. If you check a point below, then it does not satisfy the constraint. So that's the first functional constraint. Second functional constraint is x1 plus x2 is smaller than or equal to 2. That one is easier. And then we have the entire feasible solution space. And now we need to check how the line for fixed values of z looks like. So we are going to rewrite this as x2 as a function of x1 and z. So we isolate x2. So now we get this, and we can draw that line, for instance, for z is equal to 0. So that's what we have over here. The question is now in which direction should we shift this line in order to get better values for z. We would like to have higher values for z, because the question was to maximize. If z becomes higher, then you see that you have a negative number here in front of z. That means that x2 becomes smaller. And that implies that we are going to move this line downwards. And then we will get a better value for z. So it follows that this line should be moved downwards. And then the question is, how far can we move it downwards in such a way that we still have a point in common with the feasible solution space. And that's exactly up to this level. And then you will see that this x1 is 1 and x2 is 0. That's the optimum solution for this problem. The corresponding value for z is then 2. There are no points in the feasible solution space where z has a higher value than 2. This line for fixed values of z is not parallel to one of the constraints, so this is also the unique optimum solution. So only x1 is 1 and x2 is 0 is the optimum solution, and the corresponding value for z is 2.